Okay, so it's me again. You all are stuck with me. I'm Sandy Brabb, the Director of Career Services for the Voiland College of Engineering and Architecture. And we are moving on to our final phase of the Cougs In Space Forum, which is our keynote address. So first, I'd like to welcome Dr. Katie Cooper, who is the Associate Dean of Research and Geophysics faculty member in the College of Arts and Sciences, who's going to introduce our keynote speaker. Thank you.
Good afternoon, and welcome to Cougs In Space Keynote Address. I'm Katie Cooper, as Sandy mentioned. I'm the Associate Dean for the College of Arts and Sciences. I'm also a faculty member in Geology and Geophysics in the School of the Environment, and my research is focused on the evolution of planetary interiors, so I love space, y'all. The college is a proud sponsor of this year's event and excited for you all to hear from one of our prestigious alumnus, Dr. Mathew Brzostowski, which he says you pronounce Matt. Sorry, I stole your joke. Our college is the largest and most diverse in the WSU system, both in terms of breadth of disciplines, over 100 degrees across the arts, humanities, social sciences, physical and life sciences, along with mathematics, but also in terms of our faculty and alumni. We have over 600 faculty, most of whom I know their names, across the WSU system, and nearly 55,000 alumni. At the College of Arts and Sciences, we take great pride in the education we deliver in our science curriculum. We understand that knowledge and research are fundamental to both the development and understanding of human societies on Earth, as well as the exploration of space, as they provide the tools and knowledge needed to study the universe and push the boundaries of human discovery. Space exploration relies on various scientific disciplines like physics, astronomy, and the earth sciences, including geology and geophysics, to understand the origins of the universe and how it impacts our society today. Through the challenges of space exploration, it drives innovations in technology, leading to the advancements in fields like medicine, material science, communication, robotics, energy production, and computer technology, which in turn can inspire future generations to pursue science and technology careers, as is evidence in your attendance today. It also inspired my career. Now I'd like to take this opportunity to introduce Matt. Matt said he's always dreamed of becoming a scientist and astronaut, and he began taking steps toward his dreams when he attended Washington State University. He graduated in 1980 with degrees in geology and physics, which is geophysics, y'all. After moving to Texas to begin his career, Matt sought an advanced degree at University of Texas at Dallas, receiving his doctorate in earth sciences in 1991. Over the course of his 40-plus year, Matt has continued to excel in research and has 15 publications, including archiving the Apollo active seismic data, which is so cool. He's also presented on various topics around the world, including Earth model building, and most recently in 2019, the next generation planetary geophysical system. His work has been well respected internationally, which has earned 2 patents, one in methods and system for acquisition and processing for marine seismic data, and the other in method for processing converted seismic waves, which we can chat about later. And it all started here at WSU, when a somewhat younger Matt arrived on campus from Medical Lake, Washington, dreaming of being a scientist and astronaut. So please help me welcome Matt.
Wow, who is that guy, huh? Can you hear me in the back all right? Well, also, wow, what a special time for space. Who got to see the chopstick capture by SpaceX? You know, isn't that amazing, huh? If you haven't seen it, you can go out on YouTube and see it again. We have India landing on the moon. We have China landing on the moon and bringing back rock samples, geologic samples. And we have the 4th generation of rovers on Mars now. Isn't that just amazing? Okay, so full disclaimer. My wife made me say this. I am not an astronaut. Okay, I wanted to be an astronaut, And I did get an interview with NASA, which you hear about later on, but I'm not an astronaut. So if you have to leave out of a sense of despair, now is the time. No? Okay, good. Okay, so thanks again for inviting me, committee members, everyone here. Thanks for participating, take your time out from coursework and so forth. So what I'm going to do today is the committee wanted to know about my experiences and work with NASA. I wasn't a NASA employee. All the work I'd done with NASA was on my spare time, believe it or not. My vacation time, my own resources and so forth. But once again, if you want to have a goal of something, you will try to find a time to do these sorts of things. Now, to lead up to that work with NASA, I have to kind of give you a little bit more background about why it was that NASA allowed me to do things with NASA. So let's start that journey here. My first NASA picture, NASA slide. Now, some of you may recognize these people on the slide. It's probably not the best angle of them, but what you have here are the Apollo 11 astronauts returning back from their successful mission on the moon, the first humans to walk on the satellite of the moon. Over here on the right, you see the pointer, right, the arrow? Okay, you see Neil Armstrong, the commander of that mission. You see Buzz Aldrin, the LIM pilot, and you also kind of see Collins over here on the left. So this picture was taken by an 11-year-old boy just after their mission. That 11-year-old boy was me. So you may not believe this, but we used to not always have satellite communication, believe it or not. So during the early NASA missions, you would have these tracking stations. And anyone's ever watched The Right Stuff, you'll see this tracking station depicted out in Australia. One of them was on the island of Guam. My father was in the Air Force. We were based, or he was based. We were with him stationed on the island of Guam. This was one of the tracking stations. So after the Apollo mission, the astronauts traveled around the world to say thank you to everybody, and they landed on Guam. My class got to go out to the airport, Agana Airport, and see these astronauts. At that time, I already knew I wanted to do a few things. I wanted to be a pilot, a scuba diver, a scientist explorer, and an astronaut. Now, I didn't know how I was going to do all these things, but what you're going to find out through this talk today is I look for opportunities to make those goals come true. Anybody recognize this building? All right. So we're based up at Fairchild. So I went to high school, Medical Lake High School, and I loved physics and math in high school. I knew I wanted to go to college. Picked WSU for various reasons, but primarily I was able to get admitted into the physics program so I could work on a bachelor's degree in physics. And I spent 4 of my years in this building here. It used to be called the Physical Science Building, but now it's called Webster Building, or Webster Hall, right? This other building is where I spent a couple of the first years of my life at WSU, and this dormitory, Goldsworthy. It's still there, right? Anybody ever spent time in that dorm? Hopefully, okay. All right, so I entered school to get a degree in physics, but then after a year or so, you start to realize, well, you don't really get a job in physics. You really need to specialize in something, just like Katie was talking about earlier. So I took another science class. I took a geology class. And the thing I liked about physics was it kind of explained the world. I mean, you can use math and so forth, but you see physical phenomena, and you can explain the physical phenomena. You can actually predict what the physical phenomena will do, and you can use that for your benefit. So I took the geology course, and for the same reason, geology kind of explained the world. It explained why the world is made up the way it is, why you have continents, why you have sand dunes, why you have outcrops, why you have the basalt flows out here in the middle of Washington. And actually, I took a class. It was an introduction to geology class with Dr. Sorum. And I don't know if people still remember Dr. Sorum, but Dr. Sorum was the manganese nodule guy. I think he actually still has manganese nodules on campus here. He was the one that was looking to get these manganese nodules off the ocean floor. So it was an epiphany taking this class, because one of the things I learned, first off, was that 1 million years ago, all the women didn't look like Raquel Welch, and they were not being chased by dinosaurs. Now, that might date me, but essentially, this shows you that a lot of the common knowledge people have about science is wrong. And for one, we know that dinosaurs and people didn't live on the planet at the same time. But anyway, I started doing a double major, physics and geology, and I graduated that degree in geology. And during that time, I had a job in the summer. People talked about internships. We didn't have internships. We did have jobs in the field. This is me and another guy taken samples for the National Uranium Resource Evaluation. So I should ask you, are bell bottoms still in style in Washington? No? All right. So we're out here, and what's nice about this is working out in the field. That's what I liked about geology. You're out in the field. We're working in the middle of Washington. I ended up working in upstate New York as well, and I like that type of work, being out in the field, seeing nature, doing something constructive. The other cool thing about WSU is they have PE classes. So what did I say earlier? I want to learn how to scuba dive. Well, I couldn't believe it. There's a PE class you can get credit for to become a scuba diver. You actually could do your open water dive out in the Puget Sound. Fantastic. I took the class, became an open water diver. But as with any skill set, you need to continue to practice that skill set, get additional certifications and so forth. So I continued working on that. So eventually one day, and we're going to skip ahead a little bit here, I was able to scuba dive with my daughter. This is offshore Roatan. So some of the benefits of being a scuba diver as well. Now, having said that, getting time for graduation, senior, I can go to graduate school because I want to be a scientist. I want to get a graduate degree. So I applied to a couple of schools, but I also want to see if, well, can I get a job and work towards that graduate degree in my spare time? So I looked around, and on the Career Center here, they used to have a book. And I know Sandy laughed about this when I told her this, but there was actually a book where you could look up what companies were hiring different degrees. So there was a company that was hiring geologists, companies like Shell, Dowell, and so forth. But there was a company called Texas Instruments that was hiring geologists. And saying, well, why would Texas Instruments be hiring geologists? They make transistor radios, calculators, and laser-guided bombs. Why do they need geologists? But what happened was they had a subsidiary called Geophysical Services Incorporated. And this company started off after World War II doing seismic surveys, and they started developing digital equipment. That subsidiary became bigger. Actually, Texas Instruments became bigger than GSI. But what I liked about GSI was I could work out in the field. I wanted to see the world. I wanted to be out places where people probably didn't go very often. And one of those places was the North Slope of Alaska. And I thought this was cool. When I was in elementary school, we learned about a thing called the International Geophysical Year. It was in 1958. It was an effort by a lot of countries throughout the world to learn more about the Earth itself. And part of the places they worked was in Antarctica. Now, this is Antarctica, but this is the North Slope of Alaska. And where I worked there, we were about 800 miles from the North Pole. And this is not a place a lot of people go to. There weren't a lot of towns and so forth. We actually traveled there with these tracked vehicles during the wintertime, so we didn't destroy the tundra. We worked there from December until May during the winter season. In December, there was no sunshine. It was total darkness. But by the time the springtime, we had the sun all the time, where we had to wear sunglasses to protect ourselves from snow blindness. One of the cooler things that were there was we got to see the aurora almost every day in the springtime, during the night, during when it was dark. The tracked vehicles you see here, these are the seismic geophones and cables that are associated with the acquisition. This is a recorder truck here, and this is the source. It's a vibrosite source where they put a base plate on the ground, and they would send a sinusoidal signal from low frequency to high frequency, which we would correlate digital signal processing and do deconvolution to process the data. So we're shooting 2D seismic data in this area. This is actually a river we just crossed. So I get to work out in the field. So I learned acquisition techniques, and then the company wanted me to learn more about digital signal processing, so they sent me back into the processing center in Denver. And then after that, they wanted me to learn more advanced geophysics. So they sent me to a university, an internal university called Area Geophysics University in Dallas. So while I was taking advanced training, I discovered that TI had a flying club. And what did I say earlier? I want to learn how to fly, right? So they had a flying club, and get this, it was free ground school and free flying lessons. You just had to pay for the rent of the aircraft. So do I have to think about this twice? No. So in my spare time, while I did the advanced geophysical training, I got my private license. The other thing, once again, about learning to drive a car, learning to fly an airplane, you want to work on additional certifications. You want to continue to learn and so forth. In fact, this is really a little bit interesting because my grandmother, when she learned that I had my private pilot's license, she goes, well, I'm okay with you flying as long as there's a flight instructor in the class, in the airplane with you. Okay, so what do I have to do? I had to learn how to become a flight instructor, right? Okay. So one of those benefits is you get to take your dad up for flight lessons. My dad was a B-47 crew chief, 400 hours in the B-47. He never flew the airplane, so I got a chance to let him fly the airplane with me. Okay, fast forward. Now, after the advanced training, I had area responsibility for Western United States and Alaska. And I was taking graduate level classes in my spare time at Colorado School of Mines to work on a master's degree. Now, just one second. Thank you, Sandy, for knowing I needed this. Now, you probably heard about the Iron Curtain, right? But has anyone ever heard of the bamboo curtain? Okay, the bamboo curtain was a similar thing where you really didn't know what was going on in Eastern Europe or the Soviet Union, but the bamboo curtain was you really didn't know what was going on in China after the Communist Revolution, after World War II. Until Deng Xiaoping came to the United States. In the United States, he said, well, look, the world's leaving us behind. Let's open up the economy to the rest of the world, and let's invite these companies into our country, and let us learn from them, let them train us on how to do geophysical exploration. So I didn't complete my master's degree. I took a hiatus from that, but I went to China, and I got to work in the Sichuan area. Everyone's heard of Sichuan spicy food, but this is the same province. I worked in an area called Longmen Mountains, Dragon Gate Mountains. And I worked in a time when the country was just first opening up. And you can see that because we had crowds all the time watching us, foreigners. Who are these people? Are these people helping us, or what's the benefit of having these people? Here I am over here in the red and white sweater. This is the typical acquisition line we're working on. It's very complicated overthrust geology, carbonate rocks, and so forth. But we're doing advanced geophysical prospecting in the country of China. So after this tour, 84 to 87, when the country was just first opening up, I had an opportunity to do research and development back in Dallas headquarters. That's what I wanted to do. I wanted to become a research scientist. So I had the opportunity to go back to Dallas. I worked with a brilliant physicist, Harvard Ph.D., Dr. Jim Black. Dr. Jim Black, great mathematician. I was able to work with him in research, and we were developing more accurate ways to image seismic data. One of the ways we do this is with the wave equation, and don't roll your eyes right now, but the Schrodinger wave equation, which is used mostly for electromagnetic waves, can also be used for seismic waves. It can be used for compression waves, the way that my sound is projecting through the room here, and you're listening hopefully very attentively. So the wave equation, don't roll your eyes too much, it essentially takes a waveform and it expresses it in terms of, it's a partial difference equation, don't let that fool you. It expresses it in terms of space, x, y, and z, and time as long as you know the velocity. So for us in seismic data, we're recording amplitudes as a function of time with an array of geophones out there, x and y. We have x, y, and t. We can convert that into depth to know where the seismic waves come from. Now, the thing about seismic waves, they can come from anywhere when you send up the source. You just kind of have to unravel that as a function of time back into depth. That's the wave equation. So that's what we worked on. What was the challenge efficiently? And there's somebody here talking about commercialization of technology. The challenge is, can you solve these problems in a real-time effort that makes commercial benefits to your company? So you have limitations with the computers as far as disk goes, as far as memory goes, as far as CPU goes. So you have to make compromises all the time, different approximations, but hopefully enough accuracy that you get a proper solution. So we're going to go with Jim Black in the research department of GSI, but what I want to do in my spare time, I want to go to school and finish off my graduate degree. So we're right next to the University of Texas at Dallas. George McMakin ran the Center for Lithospheric Studies, and I started taking graduate classes with him. After the first semester, I told George, look, I want to finish my master's degree from Colorado School of Mines. And he looked at me and said, no, you don't. You want to skip that and go straight to your Ph.D. And of course, I'm thinking, wow, what are you talking about? Nobody does that, right? Well, very few people do that. But he believed in me, and most people that are in graduate school know this. Not only is it important that you have a good thesis, it's equally important you have a very good mentor, because he's the one that's going to say, yeah, this is a guy that's doing something unique. He deserves a doctorate, and it's his reputation as well as your reputation that's going to carry the day. So now what he wanted me to work on was that velocity problem. we have the wave equation, the image seismic data, but what are the velocities? Well, we don't know the velocity because these sound waves go down, and to image them, we have to know the velocity field. Well, there is a way to do so, and it's through tomography. Now, most of you probably have heard of CAT scans before, have seen a CAT scan. Maybe you've had a CAT scan. And you sit in this donut-shaped magnet and sit very still, and these X-rays will go from the source to the receiver. And to the attenuation, you figure out what the different cell structure is within the body. And it's doing this as a series of slices, 2D slices. And that's really what tomography means. It's imaging through slices. It's a little bit more complicated for seismic waves because we deal with refraction. If you want a good example of refraction, we actually have glasses of water there. Put a spoon in your water and look how the spoon bends in the glass of water, because light will travel with different speeds through water versus air. The same in the subsurface. Seismic waves will travel at different speeds depending on whether or not salt or sediment or granite, whatever. But through tomography, through a series of redundant measurements, we can come up with a fairly good answer about what the velocity field is. Now, it's called an ill-defined problem, that not because it makes you sick, but because there's more unknowns than knowns. You never get a perfect answer, but you get a pretty good approximation. And that's what my thesis was on for 3D tomography. Okay, so after this, I end up transferred to Houston. And what's good about Houston? Well, Houston has the astronaut corps. It's got the JSC, we call it the Johnson Space Center. Now, back to NASA again, most people don't realize that these astronauts have multiple careers. They have multiple disciplines. They're not just test pilots. Aldrin and Armstrong were test pilots. They flew in the Korean War. Armstrong eventually ended up being an engineer professor at Purdue University. And Aldrin actually had a Ph.D. in orbital mechanics from MIT. So these are guys that learn and have multiple skills. Well, the same reason that the astronauts going to the moon have multiple skills. And what you had geologists such as, this is Dr. Muehlberger, taking a group of astronauts and teaching them field geology. So check this out. And the geologists are like, you see the rock hammers they have in their hands? They got rock hammers here. They were doing real field geology here. This is Shoemaker, the Shoemaker-Levy Comet fame. Shoemaker worked for the USGS, and he's teaching field geology. This is up in Katmai, up in Alaska, where the land of 10,000 smokes is. Maybe you've heard of that. It's a Nuit Ardente geologic regime, huge volcanic eruption. But what's interesting about this diagram, he's talking to he's training these astronauts to go to the moon. He's kind of got a portrait here of what looks like an impact. And before we went to the moon, we had these craters up there, right? But we don't really know why the craters were there. I mean, they're there, but were they volcanic or were they impact craters? And until we went to the moon, we really know the difference between the two. Now, he kind of believed it was an impact crater, mostly because we have type impact craters on Earth, such as Meteor Crater out in Arizona. But you also had, finally on Apollo 17, you had an astronaut geologist, Harrison Schmitt. And he's here with Cernan, and once again, they're doing some field geology work. And you see Gene Cernan's got his rock hammer here. Now, I don't know about these plaid pants. I don't know if that was a field geologist requirement or not. I don't know if they helped him or not, but he had these plaid pants. The point was, the astronauts had to be able to learn other disciplines as well. They had to learn about geology and what to expect on the moon once they got onto the moon. So I know that my background in geology and physics, and actually my experiences with acquisition parameters, processing parameters, doing research and development, would probably be a skill set that NASA would be interested in, as well as being able to pilot in a scuba diver. So what are the opportunities now? You look for more opportunities to fulfill your dreams. This came about with being introduced to the manager of the astronaut selection office. Sounds like the guy you want to know, right? If you want to be an astronaut, talk to the manager of the astronaut selection office. This is Dwayne Ross. And Dwayne Ross here he is leading a group of astronauts, well, a bunch of other people too, on their survival training. Once you get picked for an astronaut, you go through some survival training. So this is him leading the group. And he by this time, because I'm applying every year, he's got a thick file of me already, right? But now he knows me in person. He said, Matt, come out and run with us. We run 5 miles. Come on and run with us. Okay, so I got to get up to the point where I can run 5 miles, right? Come on, run 5 miles with us, and you get to talk to the other astronauts, you get to know you interact. And it's not just that you have a skill set that they need or you learn how to fly planes. can you work on teams? And he said, look, everyone tells us you can work on teams, but let's see if these are people that you have social skills with, you can work with. So that if you're in a small room like the shuttle, and the shuttle's probably as big as this pedestal here, and you got 6 or 7 people in there, very close environment. Can you get along with each other for a few weeks on the space shuttle? All right, so I start going out there. He starts inviting me to the debriefs after each mission. I go there, listen to what the astronauts did on the space station or the shuttle, and I start talking to them and seeing more and more about the missions. And then I start working with a couple more of the astronauts. This is Drew Feustel, and he's got a Ph.D. in geophysics from Purdue University. And this is Jim Riley. He's got a Ph.D. in geosciences from the University of Texas at Dallas. So Jim's usually running with me and Dwayne. And here you see us. I'll talk more about this project later on. Here you see, this is yours truly. This is Drew. This is Jim Riley. I'm sorry, I don't remember the name of these technicians that helped us on this project. And believe it or not, this guy in the suit here is called Cosmo. I mean, what a nickname, right? Cosmo. So Drew has this idea that he wants to work on a geophysical system that we can use when we go back to the moon or on Mars. I'll talk more about what seismic we did on Apollo mission later on, but let's talk about what Drew wants to do. So Drew says, let's develop this system that we can take back to the moon. So one of the things we want to do is make it ergonomic and make it efficient and not really weight driven. Now you saw those big trucks that were carrying the cables and geophones on the North Slope of Alaska. So what he had the idea of, and this is back early 2000s. I know everyone's got a cell phone today. You probably don't know what I'm talking about, but people used to have landlines, and people used to have sometimes use a party line to talk to other people before you had these little radios we call cell phones. So he said, why don't we use a cell phone technology to get rid of the cables and just communicate with these geophones via cell phone technology, like radio technology. So we got this system together, and we wanted to test it out in the field. So NASA goes on a regular basis out to Meteor Crater in Arizona and tests various things, robotics, spacesuits, and so forth. So we got the opportunity to test this system out in Meteor Crater, Barringer Crater, 2004, 2005, 2006, recording some 2D data. The source we use, and this will be interesting later on when I talk about the sources that were used for Apollo, but we wanted to use a source that was low maintenance. So this source is essentially a steel rod, a very heavy steel rod, with a rubber band on top, elastic band, that we would slam down into a base plate, which you see at the bottom of this rod here. And it essentially works out to be a really strong hammer as our seismic source. So we're striking the Earth here along stations and recording all this data on geophones and telemetry back to a recording session. So we did this. This worked out quite well, and Drew had me process the data, which is fine. I'm doing all this in my spare time. I took vacation time to fly out there, work with Drew on this, process the data in my spare time, because I'm not an employee, and you have to remember, he doesn't have funding for a lot of this. So if he can get volunteers to help him with the project, it's all the better for him selling the project within NASA. So in addition to Meteor Crater, he said, well, look, it's not only going to go to the moon, it's also going to go to Mars. So a good type locale for Mars is Antarctica, the Dry Valley. A lot of people go off and test systems there. The Dry Valley, as its name implies, is very dry, it's very cold, and it's very remote, very hostile. So Drew goes down there with the system and records some seismic data. He's using a sledgehammer now, but the same kind of technology, cell phone technology, and he's mapping some lines across this channel field here. And they want to know how thick this channel field is. So he sends me this data, and I appreciate a lot of people don't know what seismic data are, never seen it before, but let me just explain that these are the spatial positions of the geophones, and this is time here, and these amplitudes are the reflections that come back to the receiver. And what you see here is kind of a lot of wobbles up and down, and that's because there's a very irregular near surface that has the seismic waves traveling at different velocities and so forth. So what we need to do for processing is figure out what does that channel look like, what are the velocities that we can use to correct this data, and this is what I did here, is I figured out what the velocity was, 3,500 meters per second. So let me set in context what that means. Sound waves travel through air about 300 meters per second. If you ever see a plane flying overhead, you see it, and then you hear the sound like a second or two later on, or even lightning is the same way. So air, 300 meters per second, water, it's about 1,500 meters per second. Salt's about 4,500 meters per second. So this is a pretty good velocity here, 3,500 meters per second for sediments and channel fill. I'm kind of going into detail here because later on I talk about the Apollo seismic data. I'm going to talk about those velocities as well. So knowing the velocity of that channel, I can correct. It's called static correction. I can correct for it. And you can see the nice correction here. But more importantly, I can see reflections now that correspond to the depth of that channel. So the point is that we have this geophysical system that works in Meteor Crater, works in Antarctica. It'll probably work on the Moon, probably work on Mars as well. So a little bit of success there. But having said that, I know that Apollo missions recorded some seismic data as well. So why don't I go back and look at that data, and with more modern seismic processing techniques, digital signal processing techniques, let's see if I can improve on what they learned from that data. The problem was I could get the data, but it's an original format that was recorded on the Moon. Now remember, a lot of this was very limited data, only a few channels, a limited bit, only 7-bit. Most people are really comfortable doing with 128-bit data today. And it also had to be telemetry back to Earth and puts timestamps on it. So it wasn't an obvious format to even start with. But fortunately, I found Dr. Yoshia Nakamura, UT professor emeritus, who worked on some of the original passive seismic data. He said, yeah, I'll help you. I'm very interested in this. I'm interested in keeping this data of value to the scientific community. So he helps me get the original seismic data and get into a format which we call SEG-Y format, SEG-Y format. It's a standard format that Society of Exploration Geophysicists use so that any data recorded around the world can be interchanged with anybody else and reprocessed later on. So the point was to read this data, put it into a format everyone else could use, and then using some modern techniques, see what else we could get out of this data set. So with Dr. Yoshia Nakamura's help, I should explain, his nickname was Dr. Moonquake. And the reason for that was he worked on the passive seismic data. And this is an important distinction now, passive versus active seismic. So passive means we're going to put a sensor out there and just kind of leave it there. And it's going to pick up earthquakes, on Earth it's going to pick up earthquakes or nuclear explosions, and it'll telemetry that data back to us. The same thing was put on the Moon. And there, though, it's recording moonquakes. Moonquakes due to tidal forces or maybe movement within the core of the Moon itself. But the thing is, this is a very low frequency seismometer, very low frequency specialty. And if you haven't heard already, the most that we know about the interior of the Earth is probably from seismic data like passive seismic, earthquakes and so forth. Plate tectonics, we can actually see the quakes associated with plates subducting underneath other plates. Offshore California, we can actually see we can listen to earthquakes as a Pacific plate is subducted on the continent of North America. So very low frequency, but also very low resolution, even though it can travel far distances. But what I'm interested in is the work I've done, as I explained in a long preamble here, with GSI and other companies, the active seismic, and that's a little bit different bandwidth, 3 to 250 hertz, but a little bit higher resolution, but probably limited depth. But we're only interested really in the near surface, in this case, of the Moon. What's going on with the rock layers there? So Apollo 14 and 16 had geophones, 3 geophones. Apollo 17 had 4 geophones. Okay, so active versus passive. I'm dealing with active seismic now. And the question is, how do they record this data? Anybody that's ever watched a football game, you see the quarterback, he's got this cufflink here. So he's looking at when he gets the radio signal about what play to use, using that cufflink to say, okay, this is the play we're going to play next. This is the same thing. The astronauts had these cufflinks, cuff checklists, Apollo 14, Apollo 16, and Apollo 17. And it tells them where to lay out the geophones. In a line here, a 2D line. Here, lay out a 2D line of geophones. But for Apollo 17, they have 4 geophones. They're going to put like a cross pattern. You see the cross here, geophones 1 and 2, and 3 and 4. That's how they're supposed to lay out the system. Now, what's interesting here is that it also shows the RTG. This is the power source for driving these experiments. It's a radioisotope thermal generator. What that means is it's got a hot radioisotope that's giving off heat, and you have a thermocouple associated with that gives the electricity. So it's a really common way to power spacecraft when they're far from the sun, where you're not going to have solar energy or wind energy of, say, solar cells. but you have a self-generating electric source. Okay, so now we know how the astronauts are supposed to lay out the equipment, how they're supposed to record the data. We know about the geophones, the sensors, but let's talk about the source. Okay, so on the moon there are multiple sources. This is one of them. It's called a thumper. And it's kind of a little bit like the accelerate drop or the hammer that Drew was using earlier. But here it is being tested out in Florida in the field. But essentially a long pole here, and it's got a little dial on top that goes from up to 21 initiators. And I think these are probably like almost like little blasting caps. And so it actually is going to you set which station you're on, you press the button, it fires, and it thumps to the ground. Okay, that's the thumper. Apollo 14 and 16 uses this thumper. So this is really the only source that the astronauts could use on the moon. It's fairly safe, even though it's kind of got this initiator in there, fairly safe to be used on the moon by the astronauts. But the other sources that they used, now, this is the most interesting one, I think. This one over here. This is a grenade launcher. Yeah, I'm not joking. When Mathew talks to us, they might tell me they were using rocket-propelled grenades on the moon. I said, really? Are you serious? But they did. This is a grenade launcher. And check this out. Space Ordnance Systems. Now, if anybody can find this grenade launcher on eBay or Amazon, let me know. I'd be really interested to see if I could get one of these things. So this would launch a rocket-propelled grenade, and that would the impact somewhere on the moon. That would be used for its source. Now, it says here that there was 4 explosive charges. It says here how far away they launched to. Well, how do we know that? Physics again. We're using the ballistic equation. By knowing the emergent angle and the initial velocity, we can compute with the ballistic equation how far away it's going to land. Anyone that watches baseball, if you ever wonder about how they know how far a home run is hit, it's the same equation. They got the angle of the bat hitting the ball. They got the initial velocity from the digital imagery. That's how they compute the range of that baseball. Even though they're not having somebody run out to see where it landed in the stadium, they're actually using the ballistic equation. So we have a rocket-propelled grenade on 14 and 16 in addition to the thumper. But they do the thing a little bit different on Apollo 17, maybe because of Jack Schmitt. They're going to use explosive packages. And these are going to be 8 of them. And they range in size from 1/8 of a pound to 6 pounds. 6 pounds is pretty good explosive charge, I would say. And they would deploy these fairly close at hand or up to 3.5 kilometers away. Now, I will say this. They didn't launch the rocket-propelled grenade. They did not set off these explosives when the astronauts were on the moon, for good reason. They set these off remotely after they had left the moon, for obvious reasons, for safety reasons. Okay, the other sources that they use, get this. You have the third stage, the last stage before the command module and LIM go on towards the moon. So the third stage, why do we do this? Well, let's crash it into the moon as a seismic source, both for the passive seismic as well as for the active seismic. Now, of course, they didn't crash it into the moon when the astronauts were there. They did this after they had left. Here's another source, the Lunar Ascent Module. So once the astronauts blasted off from the moon, got back into the command module, they could send this LIM back down to the surface of the moon as an impact. And you'll see we use some of these a little bit later on in the analysis. So quite a few sources here. Very creative, I would say. Yeah, we got this thing. Let's just don't keep it in orbit. Let's crash it into something and see what happens. Okay. The first thing we wanted to do when you're recreating data, and this is the great thing about science, is any scientific work you're going to do, it should be recreatable by somebody else. It should be repeatable, right? Otherwise, you're fooling people. So the first thing we wanted to do, what I wanted to do after I recorded the data, is I wanted to see if I could recreate the analysis that they did originally. So the thing I learned initially was that what they mostly did was they used direct arrivals. So let me go back here a sec. The thumper here actually has some wires, so you know T0 whenever the source goes off. Okay, so that's time 0. Then from time 0, these are 4 geophones that we're looking at here. You have time 0 here, and then after a certain amount of time, you're going to get a signal back, the reflection or the refraction from the subsurface. So they're using the arrival time, the initial arrival time, for direct arrival. So in other words, they know the spatial location between the source and the receiver. They have a certain amount of time. Okay, distance divided by time is velocity. Now they have a velocity. So they're using essentially direct arrival analysis for the interpretation of what's going on in the lunar subsurface. So let me back up again. The regolith. This is mostly what you see. You see the footprints here. You see the footprints when they're walking on the moon. This is the regolith. What is the regolith of the moon? This is not a lithified bedrock. This is actually a broken up material. The mare, the moons that you see, the black areas on the moon, the mare, the oceans, are mostly made up of basalt flows. Now, we know this now after being on the moon. The highland areas are mostly made up of northocite, a different kind of a rock. But what happens with the impacts, mostly by the impacts 4 billion years ago, is this rocks get broken up and mixed together. They're broken up. Some of them are remelted because of the impact. But also you have changes in the regolith because you have the solar wind coming down, and the solar wind is changing the composition of the rocks themselves, either making nucleosynthesis, new elements, or actually changing and breaking down the subatomic particles. So the regolith. The first velocity we're looking at, and what you're doing is you have the geophone locations here, 3 geophones. You have the thumper locations, spatial distances, and you're just measuring the time for all those geophones, and from that you connect the line that gives you the velocity from the direct arrivals. But the most interesting thing about this is you have a very low velocity, 104 meters per second. I said earlier that the speed of sound is like 330 meters per second. So why is it so slow? Well, it's not consolidated. It's not lithified. It's not a rock. It's just filled from all the impacts of the of whatever's hitting the moon. But also, you also remember there is no air there. There's no water. There's no biological processes like we see on Earth that are going to connect things together. So it is pretty much a vacuum, and it's going to be very slow propagation, just particle-to-particle propagation. Now, from the initial regolith under 4 meters per second, you have some higher velocities, 300 meters per second. So the Apollo 14 scientist, Bob Kovacs, for instance, at Stanford University, he said, okay, we have an idea of what the regolith thickness here, 8.5 meters, 104 meters per second. And then we have a deeper layer. We don't know what it is. We don't have an outcrop, but we think its velocity is about 300 meters per second. And we're going to call it the Fra Mauro Formation. Anybody who knows geology knows that when you go out to find a new rock, you name the formation after the type locale. So this is the Fra Mauro Formation. So using the thumper data, they get a near-surface model of the Apollo 14 site. And I was able to recreate this. So yeah, it looks like there's no mistakes here. It looks like they did everything the way they should have been. That looks like a good near-surface model. Now moving on to Apollo 16, we're doing the same thing. We're doing the direct arrival analysis, but now we have the impact of the thump of the grenade launcher when it launches those grenades. We also have the impact of the grenade, and we also have the lunar module ascent when it hits the moon. So we can plot those distances and times and come up with another velocity. And now we have another velocity for the regolith, 114 meters per second, 8 to 10 meters in thickness. And we have another formation deeper, higher velocity, which we're going to call Cali, even though it's in the Descartes crater area, that they name as a formation with no velocity, and they have a preferred thickness for it, 182 meters, 82 meters. Okay, so we've been able to recreate this data. Now let's move on to Apollo 17. They've laid out their geophones. They've laid out their explosive packages. The site here, this is the Apollo 17. This is an explosive package here. Here you see the South Massive. And if we look at the map of where they journeyed, this is where the most of the explosive packages are located, the geophones. This is South Massive over here. But they were able to get to that because of the lunar rover up to a few kilometers in distance. So now let's look at that data. And remember, this is not a line anymore. This is some explosive packages laid all around on the moon. We have different velocities. And when they come up with Kovacs and others, they come up with a model of the near surface. Once again, a little bit higher velocity for the regolith, higher velocity below that, 1,200 meters per second. But now if you look over here, you see an anomalous data point. It's all by itself. It's the lunar impact, the lunar module impact. And it's got a very high velocity, 4.7 meters per second. And that's why they have this layer down here, 400 meters per second. They think it's associated with the South Massive. These other two layers pretty much correspond to what we saw in 14 and 16. So this is a little bit unusual. And if you look at this data point, it's all by itself. It's one data point, kind of an anomalous data point. Well, what Dr. Yoshia Nakamura and I found out is that there was actually a timing error on this data point. And if we went back and corrected it, that data point moved up to here, closer to what we saw in the other areas, about 1,000 meters per second. And I said, okay, fine. Now people make mistakes, right? But Yoshio, he was really excited. He goes, no, we got to go back. We got to go back and fix this near surface model. He talks to Bob Kovacs. Look, we got to fix this. We made a mistake. So great for him, great for science, great for the ethics. He goes back and publishes a paper saying the timer problem for Apollo 17, and basically said this rock layer is not there. This high velocity is not there. We have these 2 other layers, but we really don't know what's going on down there. And this is a more accurate model of the near surface. So our claim to fame for redoing this was redoing the near surface model for Apollo 17. Okay, so I wanted to do additional digital signal processing. So what I ended up doing was going back and saying, well, I can do more advanced imaging techniques. I can go and process this data, do better noise attenuation. And what I ended up able to do is, rather than look at the direct arrivals, I was able to process and see the actual reflections. And the reflections, these red, blue, and green lines here correspond to those layers that they thought came from the direct arrivals. So the Apollo 16, now we have reflection data as well as direct arrival data that goes back and corresponds to the surface of the moon. Okay, now back to my dream of being an astronaut. Okay, I was able to become a scientist, able to become a pilot, able to become a scuba diver. I still want to be an astronaut. So I get a call one day at work in Houston. Early morning, astronaut selection office calls up and say, hey, do you want to come in for an interview to be an astronaut? And I'm pretty sure the definition of a nanosecond is the time it took me to say yes. So I come in for a week-long interview, and most of you probably realize that thousands of people apply at NASA, thousands, all modems of life. But what NASA will do is they will take 100, and these are all the military test pilots, the medical doctors, engineers, and a few geoscientists, and say, okay, look, we want you to come in for an interview. They break you up in groups of 10. It's a week-long interview. You come in, this is my group here, this is me. Believe it or not, that's still me. And I was with a group of, they included an MIT physics professor, a Lamont Doherty geoscientist professor, a couple of medical doctors, and a couple of NASA engineers. So pretty heady stuff. We go in because NASA wants to go back to the moon, the Artemis project, still called the Artemis project. They want to go back to the moon. Eventually, they want to go back to Mars. And what they want to do is a series of stages going back to the moon. They want to have payloads there, orbital support stations and so forth. But they want to have on each crew a geoscientist. So this is me down here, right? Me wannabe. They want to have a geoscientist on the moon for each of these missions because there's a lot of geology to still be done on the moon, the geophysics work and so forth. Okay, so this is Artemis. During the interview, we got to take a look at the capsule. This is what it looked like at the time. And in addition to that, before we get to Artemis, we have to go to the space station. We have to be able to fit into the Soyuz. So they have to make sure we're not too big, not too small, not too big to fit into Soyuz. But in addition to that, you're going to be on a space station. The languages spoken on the space station are Russian and English. Yeah, I took a couple of years of Russian at Rice University from the same professor that was teaching the astronauts. So in my spare time, I took a couple of years of Russian just so I have a little bit of background in Russian. I learned to fly helicopters. I could land a limb module. This thing you use in your spare time to accentuate your chances to become an astronaut. Now, interesting aspects of this process of the interview. You're there for a week with this group of 10. You first go in, you meet the committee. The committee consists of the people you see on TV all the time, the shuttle commanders, the space station commanders. There's HR people in there. Dwayne Ross is in there. There's some psychologists in there watching what you're doing and observing you. And they want to tell you up front, look, we want to make sure you and your family knows the risk of space travel. And at that time, there were already a couple of shuttle disasters and a couple of the cosmonauts passed away as well with accidents. But the risk of space travel at that time was the same as the risk of combat in Iraq or Afghanistan. The thing only more risky than that was being in the Army Air Corps in Europe during World War II, or on a submarine in the Pacific in World War II, or on the first wave of Iwo Jima in World War II. So, but once again, you know the risk, you manage the risk, you mitigate the risk with everything: space travel, flying an airplane, driving a car. The other interesting thing about this is that you are one-on-one with the committee. And it's kind of interesting because you start off on this committee, they say, no, I think I can talk about this, I'm sure it's changed since then. They go, okay, tell us about yourself. Starting from high school. Okay, fine. And things like, well, tell us about what aviation emergencies have you had to deal with, and how did you deal with them? Questions like that. So you talk for an hour, you meet with this committee, they take notes. Later on, you get to work out with the astronauts. They have an astronaut gym that's dedicated to themselves. You intermingle with them, you talk to them about their missions. You take a half-day psych test. After the psych test, a week later, so the NASA psychologist called me up, and this is the truth. He called me up and said, yep, you're normal. And I always tell my wife this too. So now that was a date and time. Now I don't know if historically I'm still normal, but hopefully I'm still normal. And you just you spend a week with your group, and you talk to the astronauts, and then at the end of the year you find out who gets selected. As I said earlier, I was not selected. They determined they weren't going to go back to the moon. They're going to go back to Mars. They didn't need the geoscientists at the time, which is fine. They said keep applying. That's fine. But what was interesting when I was there is that one of the shuttle commanders said, look, you're here because of your achievements. And once again, that's why I spent so much time talking about what I did to try to get to the point where you actually get an interview. They want you to have an education. They want you to have a career. Show that you can succeed in things. And then they'll question whether or not you can be an astronaut candidate. So you're here because of your successes, and it's only a matter of luck whether or not you get selected at this stage, barring being medically disqualified. The other nice thing after the whole thing, Dwayne called me up later and goes, yeah, Matt, it was really close. And that's all you really wanted to hear. You tried, you made the effort into it. I was able to make some contributions in my spare time to NASA and their mission, and that's a success I can live with. Now, I'm going to slide through real quickly. I'm going to forget about, well, two more things. The SCG had a planetary exploration task force talking about the economic benefits, the employment benefits within space exploration. So this committee was headed by Dr. Rob Stewart at the University of Houston. I was on it, Drew Forster, the astronaut, was on it, and a bunch of other people. But take a look at this. This was how much money was being spent by NASA, $24 billion in a couple of years ago, 2020. This is how much world governments are spending, total combination of $82 billion. Okay, so you know there's opportunities with governments and with NASA, but private industry is spending $272 billion on satellites, on launch facilities, on emerging industries. Now, the things about space is you don't know what industry is going to develop out there, but you know there's a lot of investment into space industries. So this should be a bonus for everyone listening in this room is there is a future in space. There's a future in space in a lot of different disciplines. You can read this as fast as I can tell you, but there's a lot of things you can do. Engineering, medical, infrastructure, HR. There's a lot of things you can do in space. So with that, I would like to say thank you for inviting me again. I tried to tell you a little bit of what I did in my spare time to help with my goals in life. I'm still flying airplanes, if you want to know more about that. And I don't regret at all my chances of not making it into the astronaut corps. When somebody asked, are you bitter about it? I like to quote another astronaut, look, you're going to get a career, and you know, those are your successes in life as well as your family. So with that, I'm going to leave some time for some questions and answers. Maybe you have a question or two, and maybe you want to challenge me with some of these facts I've just told you recently, but let's open up the questions and answers, please. You need a microphone or? I can show you another picture or two. Let me say this while you have to ask. This is what I do in my spare time now. After I retired 4 years ago, chief geophysicist for Schlumberger. You know I'm a pilot and flight instructor. I joined the Command of the Air Force, and I support their mission. Their mission is to preserve very old aircraft from World War II era, and also to educate. There's a lot of people that want to go into the military or airlines, and also preserve the history. There are a lot of veterans out there. This is an N3N biplane. It's made by the Naval Aircraft Factory. This is the only plane that the government built, the only plane the U.S. government built. It was built with spare dirigible parts. They used to be dirigibles. You may have heard of the Macon and so forth they used to have before World War II. And this is a Navy trainer that they used in World War II, and I became a flight instructor. That's what he's shaking my hand here. I can now instruct in this aircraft. The other plane I was able to fly is this Twin Beach. It was used in World War II to train navigators, and then later by the Navy to do photo reconnaissance work. But I like to give back. Taught the geology merit badge for the National Jamboree. These are our cadets. I've taken them to ground school and demo flights in this BT in the background here. This guy's already soloed in the gliders. This guy just got his scholarship to be a private pilot. These guys are going to be your future airline pilots, your future military pilots. And you still have time for your family. This is my wife here. We're on a field trip in the Philippines. This is the Bataan Island. It's far north Philippines. It's almost close to the Taiwan it is to Luzon. This is Bataan Island, and this is called Boulder Beach. So I think they're using a Wentworth scale to define this beach. Not a lot of tourists here, but these are boulders that have been ejected from this volcano, Mount Araya, in the background here. So I'm very enamored about this andesite. My wife's not so enamored. And what's interesting is you see she's got her field geology flip-flops on here. But we're having a good time together. Okay, now we have a question or two. Fact checking or anything?
Yep, back here. Oh, here, we'll start here.
Out of everything that you've done, what was your favorite?
My favorite was getting married. I tell you why. You know, you find that special person, and I told Amy my whole story about how long it took me to woo my wife, but you find that special person you want to share your life with. Someone's going to take care of you, you're going to take care of them too. When I started working on my Ph.D. at UTD, my qualifying exam, our son was born. 2 years later, when I defended my thesis, our daughter was born. The only way I could do that was because of my stability of my wife. She was a full-time homemaker. I worked full-time, and then I went to school full-time pretty much. And she was a very stable influence on my life. So for me personally, she's my best friend. She's probably my only friend. But that was my favorite time, and raising the family together. And we're still together, you see in this picture. And she accommodates my my aviation enthusiasm, my flying, my geology. She puts up with it. But, you know, she does things, too, that she finds enjoyable.
Thank you.
Hi. I had a question about your undergrad. You mentioned that you started in physics and then double majored in geology. How come you didn't finish the physics degree? Like, what drove you to geology over physics?
Yeah, that's a good question. So I wanted to double major, and I actually took all the classes that were required for a physics degree, except for, I think, gravity and relativity, quantum mechanics and gravity relativity. But to double major, you actually have more. You have to have more credit hours than what's required for just a single major. So I actually didn't get the double major because I wanted to graduate in 4 years. I really needed to get a job. So I took all the classes I needed for a physics major, but all the geology classes too. I actually had time to take graduate level geology courses, which I transferred on later on. But it's actually kind of minor. But I went back. I don't think they even listed me as a minor. But I have that strong physics background, but it's not a double major. So if you're fact checking my diploma, you're only going to see geology. Does that answer your question?
Yeah.
Okay, good.
Thank you.
Somebody over here. Yep.
So my question is, as the space industry continues to develop, is there any particular facet that you're most passionate about or looking forward to?
Yeah, I'd like to go in space. I'd like to. This is funny because I like to go to the moon. I like to go to Mars. I mean, it could still happen. Who knows? I mean, but I don't want to go pay my way, right? I want to go as a crew. And that's the way I feel about flying. I want to pay to be a passenger. I want to fly the airplanes, right? Be part of the crew. Now, that could happen. Maybe it won't happen. But my family rolled their eyes because, you know, at one time we were talking about one-way missions to Mars. Well, I mean, going to the New World was a one-way mission for a lot of people. You didn't know if you're going to survive. A lot of people didn't survive. But they kind of rolled their eyes and I said, well, I even consider that. But I said, come on, Dad, you know, we need you here on Earth. So, yeah, I'd still like to go in space, but I don't want to pay for it. You know.
And then my second question is, do you have a favorite aircraft that you've flown or been on?
Oh, yeah, okay, cool. That's a good question. That's the best question so far. All right, so I have to give you three. Sorry. You know, growing up on Air Force bases, I had a passion for flying anyway, and there's a lot of historical aircraft out there. So, believe it or not, I was able to fly a P-51 Mustang. It's out based in Florida. I was actually able to fly it. So that's one of my favorite. The other favorite, I was able to fly a Spitfire. Yeah, who gets to fly a Spitfire, right? And so it's really interesting between the two aircraft because the Spitfire was the early part of World War II. So for instance, you're hand cranking the canopy close. P-51, you push an electric button, the canopy electric closes. So quite a difference. But I tell you what's amazing about the two aircraft. You're sitting there, excellent visibility all around, perfect fighter. No wings are blocking you, everything you're around. So you really understand why they're so successful in the war. The third one is my favorite, is I got to fly a jet. And I don't mean the 707 as an airline passenger. I got to fly an L-39. This is a Warsaw Pact jet. And you know, after Warsaw Pact collapsed, there was a lot of aircraft you could buy, Yaks and so forth. This jet was built in the Czech Republic, but has a Ukrainian type jet engine to it. So I got to fly that. So going Mach 0.7. Yeah, how about that for cool, right? Yeah, I flew it. All right, sorry, 3.
Great. I appreciate the talk. You know, as someone who doesn't know a whole lot about space and what we're doing up there, you know, I have a lot of faith in our government for doing this, but there's a whole lot more private involvement in space. Can you talk a little bit about that? Is there concerns, or is this all good and just charge ahead, or what do you think?
Well, I think it's all good if you have a bunch of players interested in developing space, exploring space. The early days of space exploration was political. It was Russia against the U.S. and who had the best technology. The first satellite, first man in space. Who's going to be first on the moon? And that became a national priority. That's not so much important anymore. And what you now have is and the way a lot of technology is developed is for economic reasons. I mean, the steam engine, economic reasons because of a more efficient way to get water out of coal mines. Going to natural gas instead of using whales for fuel. Things are burning down our forests. So are going to nuclear for similar reasons, or wind or solar. It's the economic development. So I think what you see happening now, and that's why I put that private industry up there, is a huge amount of money. I mean, look at all the money people have to invest in startups, right? They have this money they made elsewhere, but they want to invest in them with a chance to improve it down the road. So that's what you're seeing happen is the economic incentive to invest in space exploration. But more like putting up satellites for remote sensing or for communication, Starlink for internet access in remote areas, or using for archaeological reasons, using laser radar to figure out where old Mayan city sites were. So I think it's really very good. I think governments are used a lot for seed money to get something going, but then you really want private industry to take over because that's going to become commercial. It's going to become more efficient. And I think you have to agree that there are still governments putting spacecraft up, but you also have a lot more private industries putting seed money into developing as well. So I think that's very good. I think you still need a core agency to kind of monitor these things and to kind of guide it. And maybe, you have DARPA for the military that you put seed money into new technology. You still need that. And you still need universities. You still need the funding for university research as well. But once you get commercial involved, once you get industry involved, it becomes a commercial efficient process. Or they're not going to survive. Yeah. You're shaking your head yes, so I guess I answered your question.
Oh, sorry. Considering how rigorous and competitive it is to sort of get a foot into the space industry, do you have any advice to stick out and sort of get involved with that?
Yeah, that's a good question. Actually, somebody asked something similar to that earlier. My freshman year at WSU, I took a couple honors classes. I took honors chemistry. And Max Roundhill, I asked him that question, are there good jobs in physics? That's my degree. And he told me, and I live by this since day one, there's always a good job for good people. So no matter the cyclical nature of an industry, how many people are out there, if you are really putting in the effort, the studies, the extracurricular activities, the skill sets, when you get a job, are you putting in the effort to really master that skill set? Are you mastering the responsibilities you're given? Are you trying to get more responsibilities? And believe me, working in the industry for 40 years, we love to see those people. The people that come in, not just do their job, show up, go home, and you know, they forget what they did the day before. But the people that come in are passionate about their job. They want to see the company succeed. They want to see their manager succeed. So if you have that attitude where you want to learn, you want to help succeed, and I'm not saying you have to burn, you know, like the panel, so you don't burn out your lifestyle. But if you're in that job, you're given those opportunities, show that they did the right decision, giving that responsibility. So don't worry about, you know, all the other people out there competing with you, or you know, am I doing something different? If you know the company is looking for a certain skill set, soft skills or hard, just work on those skill sets, and you'll get there. And you can't control the ups and downs of the industry. You can't. Oil and gas has been up and down with the price of oil every few years. I can't control that. But as long as I have my reputation, I'll find a job. You know, within a month or so, I'll find a job. And somebody else on the panel said it too. Save for the rainy day. You know, don't get too leveraged on your finances. You know, you got a job and you think you're going to have that job forever. Well, you know, make sure you can pay off the debt that you acquire, right? And you do need to have a car and house or whatever, but make sure you don't over leverage yourself as well. So when the rainy day starts, you can survive for a month or two. That's my advice. I've when I first started, I thought I was going to work for the same company forever, and then I quickly learned you're going to work for several companies. I've been laid off a couple of times, believe it or not. I've been laid off not because I did something wrong, but because it was a cost cutting in a company. They give you a package, you go find another job elsewhere. I didn't do anything wrong, but you know, it may happen that the company doesn't survive. Well, you go find another job because your reputation is there. And if you have a good reputation, they're going to come look for you too. Does that answer your question? Okay, good. All right.
Any more questions? Oh, there's one.
I guess I just want a reminder what the general requirements for being an astronaut were again.
Okay, so you have to have a college degree, and that's pretty much all that they're at. Oh, you have to be a U.S. citizen. U.S. citizen for NASA. I guess we're talking about NASA, right? We're not talking about cosmonaut. Yeah, U.S. citizen and college degree. That's a basic requirement. Most of the people they interview have a graduate degree, and they have some kind of career success already. They may have some language skills. They may know how to fly an airplane or scuba. A great movie to watch, I think I talked about this in my interview, go watch A Million Miles Away. This was an astronaut talk about his story. His family of immigrants picking crops in California, and his goal of becoming an astronaut. So he became an engineer. He got a good career as an engineer. He learned how to fly a plane. He learned how to run races like marathons and so forth. He learned how to scuba dive. So that's a common skill set that most of the astronauts have these days. Now you may not have all of them, but you have some success in your education. You have some success in your career. That's what's going to make you stand out. There's also the military test pilots, but even they have other skill sets too. They know languages, or they have another advanced degree in something. Does that answer your question? Okay. So, U.S. citizen, bachelor's degree. But, all right?
All right. Well, thank you very much, Matt, for an excellent talk today. I hope everybody enjoyed it. And we have a little gift for you.
Oh, it was down there all the time?
It is down there all the time. Thank you very much.
Thanks very much. And thanks.
Yes, give a big hand.
Thank you.
Matt.